All right, so starting a new section today, and we're going to be covering 6.3, which is partial fractions, or what's referred to as partial fraction decomposition. We're going to be doing this technique to try and solve additional integrals. These are our last type of this is our last technique for integration. So let's see where we should start here. Let's start with number 7. I'm going to work like number 7 through 39. So number 7, we have integral x to the 4th over x minus 1 dx. Okay, so the first thing that we do is make sure there's no other technique we can use that's going to knock this thing out easily. I'm seeing maybe even a substitution would probably work. If we let u be x minus 1, we might be able to rewrite this. But let's use the partial fraction technique and see what happens. So the technique is that if we have a polynomial over a polynomial, and we are going to first look to see what the degree of the top one is. So degree here is 4. The degree of this polynomial is 1 because the power on x is 1. Anytime the degree on the top is bigger than or equal to the bottom, then we're going to do long division first. So my first step for this problem is to set up long division. So I take the numerator, x to the 4th, put my denominator out here, and then I apply long division. So I have to multiply x times x cubed to get x to the 4th, so I'm going to put x cubed up here, and then I multiply x cubed here and here. So x cubed times x gives me x to the 4th, x cubed times negative 1 gives me negative x cubed, and then I come through and I change the signs here because I'm going to subtract this row. So that positive x to the 4th becomes negative, the negative here becomes positive. And now I add straight down. When I add, I get nothing left over here, but here I get x cubed. And now I repeat the process. So what do I multiply x by to get x cubed? Well, x squared. And then I multiply x squared times x gives me x cubed. Multiply x squared times negative 1 gives me negative x squared. Come through, change the signs again, add down, I get x squared. Now again, x times x gives me x squared, so I put x here. And multiply across there, I get x squared minus x. And then I change the signs again. I add down, I get x. Let's see, yeah, that's coming out on the video there. And then last one, what do I multiply x by to get x? A 1. And then I multiply over there, 1 times x minus 1 is x minus 1. I subtract, so I change the signs, add down, and I get a positive 1. So this is my remainder because x, I can't turn x into 1. So I stop when the power of what I'm left here is smaller than the power of what's here. So what I put now is plus the remainder, 1, over the divisor, which is the x minus 1. So all we're saying is that x to the 4th over x minus 1 is equal to this expression. And that means I can rewrite the integral as x cubed plus x squared plus x plus 1 plus 1 over x minus 1 dx. All right. Now, if you don't believe this, just plug in a number and see what happens, just to show that this expression is the same as this. If I take, let's say, the number 2, I plug 2 in here. 2 to the 4th power is 2 times 2 times 2 times 2. That's 16. 2 minus 1 is 1. So this should be 16 over 1, which is 16. So if I plug 2 into this, I get 16. If I plug 2 into this, I should also get 16. Let's just check. So 2 cubed is 8. 2 squared is 4. 8 and 4 is 12. Plus 2, 14. Plus 1, 15. And then 2 minus 1 is 1. 1 over 1 is 1. So I had 15 plus 1, and that's 16. So, I mean, that's not any way to be sure, just checking one number, but it makes us feel better that when we plug a number into this, we get the same thing as what we get when we plug in here. Now, the good thing is that the rewritten integral, right, is something that we can handle very easily. So we can just apply the power rule. Antiderivative of x cubed is 1/4 x to the fourth, plus antiderivative of x squared, 1/3 x cubed. Antiderivative of x, 1/2 x squared. Antiderivative of 1 is x. And then this one, notice that we have a constant over a linear expression, and we talked about this in class. That's going to be natural log of x minus 1. And that's your antiderivative. All right, number 9. I'm doing all the odds. So number 9 now. Five x plus 1 over 2x plus 1 times x minus 1 dx. Okay. Now, same thing here. We're going to think about what we have here. Maybe, try and think of some other techniques, but eventually get to the point where we're like, okay, this is definitely set up for partial fractions because I have two distinct linear factors. That's a linear factor, that's a linear factor. They are distinct because they're not the same linear factor. On the top, I have a linear expression. So it is a polynomial over a polynomial. And now I just need to check the degree. So the degree of the polynomial up here is 1. If I multiply these two together, I'd get a quadratic, and that would be a degree of 2. So the degree up here is smaller than the degree down here right now, and so I do not do long division. And so now I just go to the actual technique. The technique says what I'm going to do is I'm just going to work with the integrand first. I'm going to try and rewrite it. So I want to rewrite this as something else. And because I have two distinct linear factors, what I do is for each linear factor, I put a constant, I'll say a, here over the first distinct linear factor, and then plus the other linear factor under some other constant, which I'll call b. And so somehow there's some number that I can put here and here, there's some number I can put here and here, that when I put these together, I get back this. And now we need to go try and figure out what that number is. So what we'll do now is we will multiply both sides of this equation by the least common denominator, which is going to be this. So I multiply the left side by 2x plus 1 times x minus 1. And then I multiply the right side by 2x plus 1 times x minus 1. And what happens is this whole denominator cancels here. So we're left with 5x plus 1 equals, now over here, when we distribute, we take this whole chunk right here and we distribute it here first. This 2x plus 1 will cancel out with this 2x plus 1. The x minus 1 will still be there and the a will still be there. So I'll have a times x minus 1. And then I distribute that big chunk here. This time the x minus 1s will cancel and I'll be left with this linear factor and a b. So plus b times 2x plus 1. Okay, now we need to go and try, remember we're trying to figure out what a and b are. So I need to somehow figure out what a and b are in this problem, or in this equation to make it true. So I told you in class there's a short way and there's a long way. I'm going to do the short way, and the reason I'm going to do the short way is because there's a way that I can figure out a if I kill this off, and there's a way I can figure out b if I kill this off. So let me first try and get a. So what I'm going to do here is I'm going to say let x be equal to, and what I want to do is kill this whole thing off. So what do I need to plug in to kill this off? Well, what do I need to make x equal to turn this into a 0? So I set that equal to 0, I solve x is negative 1/2. So if I let x be negative 1/2, we know this will go away, and then we have to just see what else we're going to have. So x is going to be equal to negative 1/2. Let's go ahead and do that. So if x is equal to negative 1/2, I rewrite this. Left side, 5 times negative 1/2 plus 1. And then I rewrite the right side equals a negative 1/2 minus 1. That's this. And then we already know if we plug in negative 1/2 here, this whole thing goes to 0. So it's gone. And so now I have a linear equation. The only variable I have in here is a, so I'm going to solve for it. So here we get negative 5 halves plus 1 equals, let's put these two together. So a times negative 3 halves. And add these two together, negative 3 halves equals, let me just rewrite this, it's negative 3 halves a. And now to get a by itself, I divide both sides by negative 3 halves. And that's going to be real nice, because when I do that, this is a 1, this is a 1, so a is 1. All right, so I know what a is. All right, a is 1. The next thing I'm going to do is now try and go and get the b, and to do that, I will kill off this term over here. So to do that, it's pretty easy. Just make x 1, and that's going to be 1 minus 1 is 0. So I have to start over again. Remembering a is 1. I'm just going to write that down up here so I remember it. A is 1. And now I'm going to let x be equal to 1 right here. That way it'll kill this off. If I do that and I rewrite this line, I get 5 times 1 plus 1 equals, now remember this is gone, but then I have plus b times 2 times 1 is 2 plus 1 is 3. So I get that. And then cleaning this up, this is 5 plus 1, that's 6. 6 is 3b, which means b is 2. And once I know that b is 2 and a is 1, I can rewrite everything. Remember, this expression in here turned into this thing. I erased it, but I'm going to rewrite the integral right now. So we know that this integral equals integral, and then two things. We had 2x plus 1 here, plus over here x minus 1. A was on top of this one, and a was 1. B was on top of this one, and b was 2. And that is ready to go, because what I have now is I have constant over a linear expression, constant over linear expression, addition between them. I can integrate each one by one. So this equals antiderivative. I know that this is going to be the natural log of this. But because I had a 2 on the x, I have to scale by that. So 1/2 is out front. We did this with sine and cosine, and I'm sure I showed you in class too how you have to take care of that a in front. And then the next one plus, now the 2, I can just bring the 2 out and imagine, you know, that was like a 1 here. And so I have 2 natural log of the x minus 1. I don't have to scale by anything there because there's a 1 in front of the x. So that's it. Okay, let's look at 11. My gosh, someone's watching a movie or something in a classroom. It's loud. Wish we watched movies. That'd be cool if that's all we did is came in and watched movies. All right, so this is a definite integral. Remember, we're ignoring the numbers here. 2 over 2x squared plus 3x plus 1. Now, there are a couple of approaches to this problem. If you see a constant over a quadratic, if it's irreducible, we complete the square. But I believe we can reduce this because I believe this factors. So let's try that first. We have 2 over, let's see, I believe we've got 2x, x, plus 1, plus 1. Let's just check. We get 2x squared, then we get a 2x, and then an x, that's 3x, and then we get 1 times 1 is 1. So that's it. And now I go through and I play this game. I say, all right, I've got to get this integrand to be equal to, since I have distinct linear factors, a over 2x plus 1 plus b over x plus 1. So same game we just played on the previous problem. I multiply both sides by the LCD, which is this. So I multiply it over here, everything goes away, we're left with 2. Multiply this over here, I think I'll write it down for you, 2x plus 1 times x plus 1. I'm going to multiply that entire right side, so it's going to go here and here. When it goes from here to here, the 2x plus 1's cancel. I'm left with a times x plus 1. When I multiply here to here, the x plus 1's cancel. I'm left with b times 2x plus 1. My goodness. All right. So this one, I think I'm going to not do the short way, just so you have another example of how to do this. The short way, I would kill off the b to get a, and then to get b, I'd kill off the a. So let's just talk about what you would do. First thing I would do is I would let x be negative 1/2, and that would kill this off, and then I'd figure out what a is. And then to figure out what b is, I'd let x be negative 1 and figure things out and get my a, and get my b. But that's the short way. I'm going to show you the long way. Long way, you distribute everything out. So here, so ax plus a. Distribute here, so 2bx, and then 1 times b is b. And then what we did was we grouped together our x terms, ax plus 2bx. So those two are x terms, I put them together. And then I group my constants, which are these two numbers out here. Then the ones that are like terms here, I factor out an x. And what I'm going to do is I'm going to put the x behind it, you'll see. So this plus, and then I like to put these in parentheses just to have them. Okay, so I pulled an x out of here, but instead of pulling it out front, I pulled it in the back. And that's just because I know this is a number, and it's a number in front of x, and that's the way we normally write it. So now what I have to do is I have to match the left-hand side and the right-hand side. So notice on the left-hand side, I don't have any x's over here. So you can imagine that in front of this is 0 x's. And that means that if this left and right-hand side have to be equal, 0 has to be equal to the coefficient out here. See, the number in front of x has to be equal to the number in front of x over on this side. So I know that a plus 2b has to be equal to 0. Additionally, the number by itself, which is these two, right? These two must be equal to that number. So what I've done is I've set up two equations. The first one says that a plus 2b equals 0. The second equation says that a plus b must be equal to 2. And then now I have a system of equations. And you can solve this by elimination, or you can solve this by substitution, or you can use your graphing calculator to do it. I'm going to do it by elimination. So what I'm going to do, I'm going to kill these a's off by rewriting the system of equations. I'm going to multiply the top row by negative 1. Okay, so if I multiply that by negative 1, I get negative a minus 2b equals 0. And then leave the second row alone. And now I add straight down. So I did that so that the a's would cancel when I add. So I add down, I get nothing. Add down here, I get negative b equals 2. And if negative b is 2, whoa, how far off am I over there? Well, I'm really close. Really, really close. Oh, whoa, I'm off. Oops. I forgot that I had a finite board here. Let me see here. Wow, I went way the heck out there. Sorry about that. Let me rewrite this piece. So what I was doing was these two right here, setting up a system of equations. I think I'll do it up here. Okay, so setting this up, I got a plus 2b, it's Monday. 2b equals 0, and then the other equation, a plus b had to be 2. A plus b had to be equal to 2. And what I said is to get this to work, I want the a's to cancel, so I multiplied top row by negative 1. I get negative a minus 2b equals 0 times negative 1, which is still 0. Then a plus b is 2. So I don't change the second row. And then I add down. If I add straight down, the a's cancel. Here I get negative b equals 0 plus 2 is 2, which means b is negative 2. So I know what b is now. Once I know what b is, I can go into this equation or this equation or this equation or this equation and just replace b with -2. So I'm going to just go to this equation, rewrite it, a plus b equals 2. Now I'm going to replace b with what I know it is. It's -2. And that's really a minus 2 equals 2, and then add 2 to both sides, a is 4. So I know what a is 4. I know what b is -2, and now I rewrite the integral. So when I rewrite this integral, I get two pieces here. I have a, it was a over this, so a was 4, so 4 over 2x plus 1, and then plus b, which was -2, over x plus 1. All right, now at this point I can do my integration. Let me just check this here. Oh. All right. Let's do my integration. Do this one a little slower. This 4 constant over linear, I know I'm going to be using natural logs. I'll pull that 4 right here out. I know I have natural log of the bottom, 2x plus 1. But then because there was a 2 there, I have to scale by that, so 1/2. And then I have plus a -2, so let me pull the -2 out. I know I have a natural log. I know it's the bottom, x plus 1. Running out of room here. And then plus a constant. I don't have to scale because that's a 1 in front. So my final answer is, let's see, 4 times 1/2 is 2. Natural log, 2x plus 1. And then over here, -2. Natural log, x plus 1 plus c. All right, let's look at 13. So far, everything we've done, we've had distinct linear factors. Well, the last two that I did, distinct linear factors. Let's see what this one is. Ooh, ax over x squared minus bx. Yeah. Okay, so we do have a polynomial over a polynomial. Remember, the variable here is x. A and b are just numbers. Now, don't confuse these a and b's with the capital A and b that we've been finding. This is a problem where they just don't tell you what those numbers are. It could be 5x over 4x right here, or over x squared minus 4x. So just treat those as constants. But we do have first power here. We have second, so we don't need long division. Man, I could try basic substitution here, because I know that if I let this be u, it's quadratic, the derivative is linear. But let's stick with the technique of this section. Let's try to factor the bottom, x, then x minus b dx. And if we do that, we do have two distinct linear factors here, right? This is a linear factor. That factor is actually the factor x minus 0. And then the other one is x minus b. But it's two linear factors and they're different. So what I'm going to do is I'm going to try and rewrite this integrand with something a, capital A, over the first linear factor plus some b, which I'm going to find, over the second linear factor. And then we multiply both sides by the LCD, which I'm not going to show. We'll get the ax here. Here we get the a, and then the x minus b will be left, and then plus the b, and then when the x minus b's cancel, you get x. So that's what we've got. Now, let's use the short technique, all right? Let's kill off this. To kill off that, I'm going to let x be 0. If x is 0, the left side is 0. This is a times 0 minus b is going to be a times negative b. And then over here, we know that that went away. So what you're getting is, what, 0 equals, this is weird, negative b times capital A, and we're trying to find out what capital A is. We divide both sides by negative b, and we still get zeros A. All right, this is not looking good, all right, because what we're saying is that this is going to be a 0, and if that's a 0, then that's not going to appear in our new integral, and that's a major problem. But let's stick with it and see if this generates anything. So I want to kill off this term now. To kill this off, I need to let x be little b. If x is little b, then we come over here, write the left side, a little b, right, a times x, but x is little b, equals, we know this is gone, and then this is going to be capital B right here times little b. And what that tells me, remember I'm trying to solve for capital B, I divide both sides by little b, I'm getting this. Right, divide both sides by little b. So capital B is little b, and then that's 0, right? So that doesn't make a whole lot of sense, because what we're saying here, let me get this out of here. What we're saying is that this original expression can be written as 0 here, and then capital B is little a. So what's going on? It seems like this can't be possible, that this just doesn't make any sense. But look, let me show you what this actually turns out to be. So we're saying that ax over x times x minus b is equal to 0 over this, which is 0, and then this right here. That's going to be little a. Capital B is little a. This is confusing. So little a over x minus b, right? How's that possible? Well, we could have seen this in the very beginning, and should have seen this in the very beginning. These x's cancel, and then all you have is this, and we're done. But again, this kind of shows you the progression of how you do that shortcut. If we would have just started the problem and realized that those canceled right in the very beginning, if we would have just said, hey, look, cancel the x's, then that's where we would have been. But see, the partial fraction technique actually got us to that at the same, doing it got us to the same expression. Now this is pretty easy to do because the a can come out because it's a constant. Integral 1 over x minus b dx. This is a constant over a linear expression. The antiderivative of that's going to be natural log. I don't have to scale because there's a 1 in front of the x, but I had an a on the outside. So this is going to be a times natural log absolute value x minus b plus some constant. So we could have knocked that out in the very beginning a lot easier, but again, just wanted to illustrate how the technique works. All right. 13, let's look at 15. 2x plus 3 over x plus 1 squared. All right, this problem is a little bit tricky because when you look at it, you're like, okay, I've got linear expression on top, so the power is 1. On the bottom, if I multiplied that out, that'd be quadratic. So you'd be thinking, I don't need to use any sort of long division first. But remember that if you have a linear factor and it's repeated, right? So if we have a repeated linear factor, then what I'm supposed to do is try and find a way of rewriting that integrand, right? In a way that I get, first of all, an a over the linear factor by itself, just one factor of it, then plus, now instead of b, it's bx over the linear factor, I'm sorry, not bx, just b, over the linear factor squared. So somehow I'm supposed to turn this into this. All right, so if you have a repeated linear factor, if this is a 2, you do a over that, then b over that squared. If this were cubed, you do a over that, b over that squared, c over that cubed. If this was to the 4th power, a over that, b over that squared, c over that cubed, d over that to the 4th power. So if I can turn this into this, I should be able to integrate each of these, because we did look at those. Constant over linear, I can integrate. Constant over linear squared, I should be able to integrate also with a basic substitution. So let's try this. I multiply both sides by the LCD, which in this case would be x plus 1 squared. Cancels on the left, I get 2x plus 3. On the right, when I multiply x plus 1 squared through to both of these, here to here, notice that when I do here to here, only one of the factors cancels. So I get a times x plus 1. And then if I multiply here to here, they both cancel, and I get just b. And now we have 2x plus 3 equals, now you could try the killing of things off, but I'm going to go the longer way. Ax plus a plus b, so I distribute the a through. And now I'm going to play a matching game. What's the number in front of x supposed to be? It's supposed to be a 2. What are the two numbers out here? They're supposed to be a 3. And so I'm ready right here. I know that a is 2. I know that a plus b is 3. But if a is 2, then this is 2 plus b is 3, which means b is 1. So I know what a is, I know what b is, and I can rewrite the integral now. So this integral becomes, all right, a over x plus 1. So a was 2, so 2 over x plus 1. And then plus b is 1 over x plus 1 squared dx. All right, so now let's integrate this. The first one should be pretty clear, pretty clean. 2 comes out, natural log absolute value of x plus 1. This one, on the other hand, you cannot use natural log because it's squared, but we can still handle it. And I'll do it on the side here just so you can see it this first time. In the future, I won't mess with it. I'm trying to integrate 1 over x plus 1 squared dx. I can make a quick substitution. U is x plus 1. du is dx. Rewrite the integral 1 over u squared du. This is going to be negative 1 over u when you take the antiderivative, because we've done that so many times. So this is going to turn into negative 1 over u, but u is x plus 1 plus a constant. So check it for yourself. If you differentiate this, you get back this. All right, that's it. It's number 15. There is another way to do this, but we'll mess with that later. 17, but looks nasty. Integral four y squared minus 7y minus 12 over y times y plus 2 times y minus 3 dy. So sit there and look at that for a little while. We do have a polynomial over a polynomial. The degree of the numerator is smaller than the degree of the denominator, so I do not need any long division, thank goodness. All right, this is going to be, like if you multiply it all out, it's going to be y cubed. The top is y squared, so you don't have to worry about that long division. Now, what are the chances that this thing factors and one of these cancel? I doubt it. You could check it yourself. I'm not going to, but I'm going to say I'm seriously doubtful that this cancels with anything. So I'm going to proceed as if it doesn't. Okay, so I have 1, 2, 3 distinct linear factors. So what I need to do is try and rewrite this and take care of my distinct linear factors as follows. So I write 4y squared. I'm just going to rewrite the integrand. And for each distinct linear factor, I need what, a over the first distinct linear factor. I need b over the second linear factor. I need c over the third linear factor. And now I just need to come up with a, b, and c. So we have three things we're looking for. I multiply both sides of the equation by the LCD. So here it cancels completely. I get 4y squared minus 7y minus 12 equals, now when I multiply this times that, just the y's cancel, and these two are still left with the a. So I get a, y plus 2, y minus 3, plus, now when I multiply this factor, this whole thing times this, the y, that should have been plus 2, I'm sorry. When I multiply this times the y plus 2, this thing here, the y plus 2's cancel, so I get the b, I still have a y there, I still have a y minus 3. And then finally, when I multiply this times the LCD, the y minus 3's cancel, I still have the c, I still have a y, I still have a y plus 2. Oh man, okay, so how in the world are we going to figure out what a, b, and c are? Well, we could do the long way, distribute all that through, or we can see if it's possible to kill things off. So is there a way for us to get a? Well, we would have to be able to kill off b and c at the same time. And to do that, I can't use the y minus 3 and the y plus 2 because I can't kill off those simultaneously. But if I let y be 0, I'm going to kill off both of those, and I won't kill off this. So let's do that. I'm going to let y be equal to 0. Let y be equal to 0. Let's see what the left side turns into. Very nice, negative 12 equals. Now remember, y being 0 here kills it, y being 0 here kills it. Let's plug in y equals 0 here. So we have the a, then the first parentheses, I get 0 plus 2 is 2, and then second parentheses, 0 minus 3 is negative 3. And now if I multiply those together, I get negative 6, and I divide through, I get a is 2. Oh man, that was nice. Okay, next one. Let's try and get b. To get b, I can't let y be 0, obviously, because it'll kill off b. So I need to somehow preserve b and kill a and c off at the same time. And notice that a and c both have the y plus 2 factor, but this one doesn't. So if I can make this factor go to 0, I'm good. So how about y being negative 2? It'll kill this off, it'll kill this off. So that's my next choice. Y is negative 2. Okay, now the left side, be careful here. You have to plug in negative 2 into this. So negative 2 squared is 4. 4 times 4 is 16. Okay, negative 7 times negative 2 is 14. And then minus 12. 14 minus 12 is 2. Plus 16 is 18. So the left side should be 18 equals. Now remember, when y was negative 2, it killed this one off. It killed this one off. And so I just need to plug in negative 2 right here. So I have b. Y is negative 2. Negative 2 minus 3 is negative 5. Okay. That's not nice. Double check that, yeah? 14, 2, 16. I'm just hesitant because this is not a nice number. 10 and I divide through. Just double check before I go too much further because I don't want to run into a problem here. Seems a little bit early for them to be giving a fraction. What number was this? Oh man. Not gonna be able to check it right away. Well, we can check it a different way, but let's just continue. These two multiply to give me 10. Divide through, I get 18 over 10 is b, and that's what, 9/5 is b. So b is 9/5, a is 2. All right, let's try and get C now. So how can we get C? We want to preserve C and kill these off. To kill these off, they both have a y minus 3 factor, so I'll let y be 3. So that'll be here. Y is 3. All right, so let's see, y being 3 here. 3 squared is 9. 9 times 4, 36. Y is 3. Minus 7 times 3 is 21. Minus 12. 21 minus 12 is negative 33. 36 minus 33 is 3. So 3 on the left side, and then what? These two are gone, gone, gone. Replacing y with 3 here. So C times 3 times 3 plus 2 is 5. So 3 equals 15C, which means we divide through, we get 1/5 is equal to C. So I got another fraction, so I'm feeling a little better that maybe they do have fractions in this problem. All right, so now we know what A, B, and C are. We should be able to rewrite the entire integrand. Okay, so this integral will become this big thing. A over our first linear factor, which was y, plus B, B was 9/5. Now watch the way I write this. 9/5, that's B over my second distinct linear factor. Plus C, C was 1/5 over y minus 3, which was my final linear factor. And then at this point, I'm ready to integrate. All of those are constants over linear expressions. So I should be able to do natural log on all of those. So let's see, the 2 comes out, 2, and then we've got 1 over y, so natural log y. Plus the 9/5 comes out. So that 9/5, I just drop it out front. 1 over y plus 2, antiderivative, natural log of y plus 2. And then 1/5 comes out. Antiderivative of 1 over y minus 3 is natural log of y minus 3. None of those had to be scaled because all of them had 1s in front of the y's, and so that should be it. Now let me do a quick check of something here. Where's 1? I'll have to check that later. I can't check it right now. It's going to take too long. All right, let's look at number 19. How much time is this video? 45 minutes. 19. X squared plus 1 over x minus 3. X minus 3 over x minus 2 squared dx. I'm going to do all these odds, and I doubt I'll have time, but I'd really like to come back through and do the evens. All right, so polynomial over polynomial, degree up here is 2. If we multiply those together, the degree would be 3, so no long division is necessary. I have a distinct linear factor. I have a repeated linear factor. Sure, I wrote this down right. Yes, I have a repeated linear factor, so x minus 2 times x minus 2 because it's squared. So what I know is that I must be able to rewrite this integrand with, okay, for a distinct linear factor, I need an a over that distinct linear factor. Plus, now for a repeated linear factor, I need a b over the x minus 2, and then a c over the x minus 2, but this time squared. And remember, if that was cubed, then I would have a d over that linear factor right here, cubed. So that's it right there. Now, let's try this, multiply both sides by the LCD. So when we multiply this over on this side, everything goes away except for the x squared plus 1. That's always going to happen. Now let's be real careful. This times this, the x minus 3's cancel. you're left with a, and then the x minus 2 squared is still there. Maybe it'll help if I actually write this in here. If I take this and I multiply by x minus 3 times x minus 2 squared on this one, the x minus 3's cancel, I'm left with a times that. Then I have to do the same thing here, x minus 3, x minus 2 squared, right? So I'm going to write two of them just so you see this. One of the x minus 2 cancel. I'm still left, though, with a b, an x minus 3, and an x minus 2. And then when I multiply this one times x minus 3 times x minus 2 squared, this and this cancel completely, and I'm left with c, x minus 3. All right, so let's see if there's a way we can do this easily. I'm trying to find a, b, and c. So is there a way to get a? Well, I need to be able to kill these two off. Both of these have the x minus 3 factor. This one doesn't. So if I let x be 3, I'm going to be able to kill those. So let's do it. Let x be equal to 3. This left side becomes 3 squared is 9 plus 1 is 10 equals, if x is 3 here, 3 minus 2 is 1, 1 squared is 1. So we get just a times 1, which is a. And then everything else is gone. So I know a is 10. Okay, how about b? Can you get b? Well, to get b, I got to be able to kill off a and c, but see, these don't have anything in common. So it's impossible for me to kill off a and c simultaneously, because I can't let x be two different things at one time. So there's no way to get b by itself. How about c? Can we get c? Well, to get c, I got to kill off these two. And to do that, I can let just x be 2. If x is 2, it'll kill these off, but it won't touch this one. So even though I can't get b, I'm going to be able to get c. Let's let x be 2. If we do that, the left side, 2 squared is 4 plus 1 is 5. This is gone, and then over here, if I let x be 2, 2 minus 3 is negative 1, so this becomes negative c, and that means c is negative 5. So I know what a and I know what c are, but I don't know what b is. So what do we do in this case? Well, you have a couple options. You could just go back and distribute this all through and then do the matching game, the long technique. Okay, or you can just replace these a's, the a and c right now, and then multiply it all out and see what you get. Either way, there's no shortcut, super shortcut for this one. So what I think I'll do is I'll illustrate how that long technique would work in this problem. So I hope you understand, we don't know what b is. We know what a and c are. So I'm kind of stuck. So I'm going to make a note over here so I can check this. I'm going to use a different technique, the longer one. When we do that, we should get the same answers. Okay, so what I would do, if I would have recognized in the beginning that I'll never be able to get b, is multiply this all out. So first foil this out, x minus 2 times x minus 2, and then distribute an a through. And I think I'll write that. I'm going to erase this. I'll come back to it because I'm going to need a lot of room here. So the left side's x squared plus 1 equals, okay, multiplying that out and then multiplying by a, you get a x squared minus 4a x plus 4a. So this multiplied together is x squared minus 4x plus 4, but then distributing an a through, you get that. And then here, when you multiply these two together, what? You get x squared, then you'll have a b, so bx squared. And then this times this times this, that'll be a negative 5x, but then times b, so negative 5bx. And then the last term's negative 3 times negative 2 is positive 6, but then times b, so 6b. And then your last one, cx here, and then minus 3c. All right, so at this point, I will collect all my x squareds together, which is this one and this one. I'll put them together. I'll collect all my x terms, this one, and this one. So I'll have minus 4ax minus 5bx plus cx. And then I'll get all the things that don't have x's in them, which are those three. So plus 4a plus 6b minus 3c. All right, now what we do, left side still x squared plus 1, is I will factor out what's common. So in these two, I pull out an x squared, I place it in the back. Over here, those three have x's in them. I'll pull the x out. Now watch what I do here. Plus, in parentheses, x. And I put these three things. Negative 4a minus 5b plus c. So even though there's a minus here, I say plus and then put the minus here and here for those two and then plus here. If you distribute that x through and remove the parentheses, you'll get back this. Here, I do plus, and it's just these three together, which you don't need in parentheses, but I like to put them in parentheses. That way I have three groups. I have this, this, and this, and that should match up with what we've got on this side. Now keep in mind, the number in front of x squared here is 1. I do not have an x term, so it's like a 0x, then plus a 1. And what we're going to do is play a matching game here. I know that 1 must be a plus b, right? The coefficient in front of x squared has to be 1. The number in front of the x, which is all of that, must be 0. And then this number right here, 1, must be these three together. So let's put this together. I have three equations and three unknown variables. So let's write down the system here. Connect that up there like that. Okay, so my system of equations looks like this. First of all, a plus b must equal 1, and that's from this. A plus b must equal 1. Notice I left a little bit of a space here for c's, because c's are going to come in on the next equation, so I left a column here for c's. Next one, negative 4a minus 5b plus c must equal 0, because these three together must be 0. And then finally, 4a plus 6b minus 3c must be equal to 1. And that's because these three must equal the number by itself. All right, well, this doesn't look fun. So this is where you could get on your calculator and do an elimination using matrices or your RREF function on your calculator. I'm going to do this one by hand, but I'm going to cheat a little bit because I already know what A and C were from earlier. So if I know what A and C are, that's going to really help me clear out everything and get my B, because that B is really the only thing I don't know. So let's look at that first equation. Right, A plus B has to be 1, but I already showed earlier that A had to be 10. And that, I'm done, because subtract, you get B is negative 9. And that was the only thing I didn't know. But let's just check this, okay? Check this out. Let's just see if this is A, B, and C, if all three of those equations are satisfied. So first of all, A plus B is 1. Well, 10 plus negative 9 is 1. That's true. So that's good. Right, how about this one? Negative 4 times A would be negative 40. Negative 5 times B, but B is negative 9. Negative 5 times negative 9, what is that? Oh, I can't do simple math right now. Plus 45. Plus C, C is negative 5. And look at that. Negative 40 plus 45 is 5. Take away 5, we get 0. So the second equation checks. And then let's do the last one. 4 times A, that's 40. 6 times negative 9 is negative 54. And then negative 3 times C, that's negative 3 times negative 5 is 15. So if you put these two together, you get negative 14, and then plus 15 is 1. So they all check. So I'm feeling real good about that answer. Okay, but I've kind of lost track of where I am. Let's go back to the original integral. I know what A, B, and C are. Okay. So the original integral turns into a over x minus 3, and a was 10, plus b, which we said was negative 9, over x minus 2, and then plus c, which was negative 5, over x minus 2 squared. Constant over linear, constant over linear, constant over quadratic. This one we did earlier, I can do that one. So here's my answer. 10 natural log absolute value x minus 3 minus 9 natural log absolute value x minus 2. And this turns out to be plus 5 over x minus 2 plus c. So when you take the negative 5 out and then do your little integration substitution, you get another negative that pops out, and it turns that negative 5 into a positive 5. You work that yourself. This comes from here. That's it. I think this is going to be where I cut the video. Let me just double check that. .3. That was number 19. Yep, we're all good. Okay, I'll do another video in a little bit.